everyone, and welcome back to the Infodump, the series where I do a deep but not necessarily scholarly dive into a particular topic. This week we are continuing on with our previous topic of physics, and of course we are now into the actual meat of physics rather than the fleshy exterior. I don't know where the fuck I'm going with this. Yeah. Anyway, you may also notice if you're watching the gameplay, I'm still on the same level of Space Chem. That's not going to change for a while. This is a fucking hard one. It's the wall that made me stop playing in the first place years ago. So, pretty understandable why I would just smash my head against a wall. And yeah, I will eventually figure out how to surpass it, but at the moment I don't want to dedicate like 10 straight hours to trying to figure it out and pull it off, in part because I don't want to take up all that space on my hard drive from the 10-hour file, and in part because it would mean dedicating 10 straight hours to something, which I don't do. So, that out of the way, back to the actual, content, physics. So, the thing about physics is it's really, really, really complicated and branchy. And that is something that I sort of realized as I was sitting down to put together notes and get ready to record this episode, because I had to decide what I was actually going to do it on. And I think the best place to do it would be to start with what exactly a fundamental particle is. And then we will build up from there. So, fundamental particles, which is a term you will hear a lot in physics, are particles that can't be split into other particles. So, atomic nuclei for a long time we thought were indivisible. Then we learned that in fact they were made up of protons and neutrons, which we thought were indivisible. But it turns out that those are made up of quarks held together by gluons, which are the force carriers for the weak nuclear force. Now, a fundamental particle, generally speaking, does not refer to a force carrier particle per se, but rather to another type of particle. And those can be classified into a few different categories, but the key thing is that they are the manifestations of probability fields that give rise to these particular particles. That's a that really goes to show just how much goes into my writing for this. But yes, these particles, the only way that you can break them down at all is by making them decoherent, by turning the condensation of probability that is the particle into a sort of flat probability, so the particle doesn't exist anymore. You sort of shove it back into the waveform, as it were, which, if you haven't watched episode 9, which is where I talk about waveforms and the probabilistic nature of everything, that, if you haven't watched it, that won't make much sense, so you should probably go and watch that if you've been skipping around and not really watching everything in order. It is in order for a reason. So, the most fundamental particles, that is to say, the ones that make up the most stuff, are quarks. Now, more fundamental isn't really the best way of putting it. It's more that they are the most common fundamental particles, because Each proton and each neutron has 3 quarks in it. The flavors, as they're called, the different types of quarks, determine what particle is created. That's also where you get the antimatter equivalents of those protons and neutrons. Sort of. It's more complicated than that, but antimatter is something that we still don't 100% understand. We know how to make a lot of it, but we don't understand why it exists or has the exact properties it does. Or maybe we do and I just haven't come across that research. But anyway, regardless, that will be for a future video. Right now, I am just trying to build on what we talked about the last couple episodes. So, the different quarks, when put together, create all sorts of different particles. So quarks are one category of fundamental particles. Another category, the second most common, are leptons. This is the category that electrons fall into, as well as muons and neutrinos, and so on and so forth. They are very common, but not quite as common, at least as far as I am aware, as quarks are. Which, you know, the universe is random, so of course there's not going to be an even distribution between different things. Either way, the key thing to know about these leptons and quarks is that they are the bedrock of how things work, fundamentally speaking. Their interactions between each other and within the groups is, well, what gives rise to just about every necessary interaction to have anything at a complex level. When you think about it, that makes sense. You can't have a universe more complicated than a single fundamental particle without particles interacting. So of course, the way that they interact defines the reality that they create. So, the fundamental particles, in total, not counting the force carriers, because those are sort of their own thing off in the corner, not interacting with the Higgs field, except for the Higgs boson, which is its own whole thing, but they don't have mass, they're their own thing anyway. Quarks, the 6 flavors, are up, charm, top, down, strange, and bottom. Leptons are also a set of 6. Electrons, which you've almost certainly heard of. Muons, taus, electron neutrinos, muon neutrinos, and tau neutrinos. Technically speaking, you can just lump those last 3 all together as neutrinos, because there is not a huge difference between the different kinds of neutrino. Once you get into the nitty-gritty, yes, there is, but the defining factor of neutrinos is that they hate interacting with anything else. Just as a rule. The only places that you really see the different types of neutrinos and like the difference there being important is when you are actually trying to work out the exact, well, particle physics of a subatomic particle reaction. So if you're trying to, use the Large Hadron Collider, say, to smash particles together and see what comes out, then you want to be able to tell, even if only by equations and such, what exactly is coming out the other end. So, of course, even with all of that, there are still a great many particles out there that we might not have detected. The neutrinos are, like I said, famous for their hatred of interacting with anything. So it could be that there are other particles out there that are even more loath to interact with anything else than neutrinos are, thus resulting in a completely undetectable particle, or a particle that is so unlikely to be detected that the odds are very much against it ever being detected through the lifespan of the universe. Either way, whether there's more out there or there isn't, we still don't understand anywhere near enough about how all of these fundamental particles work, how they come to be, aside from just that pure randomness, and how they, well, behave in the ways they behave. How it is that an electron can have its precise level of charge that no other fundamental particle really has the same of. So, of course, all of that is just to sort of lay the groundwork for what we're going to talk about next. As I said, the interactions between the different particles are sort of defined by those four fundamental forces that we talked about previously. Those forces, I'm not going to go over them again, but they shape every single interaction, particularly the weak and strong nuclear forces when it comes to the quarks binding together and then their products interacting with each other, but also in the case of leptons, particularly the, well, electromagnetic force, since that's, well, you can probably guess from the fact that it shares a root in part with electron that there is a strong link there. And of course, the gravitational force, ellipses question mark, we think it's a force? Maybe? Who fucking knows? That is the one that they all equally interact with. Because, well, if they have energy, if they have mass, then they alter and warp space-time around them, creating gravity. Ellipses question mark. Look, a lot of stuff around gravity while we're dealing with quantum mechanics is just going to be an ellipses question mark. Because, well, welcome to quantum gravity. It's just an ellipses question mark. Nothing more to it. Nothing else there. Just, we don't fucking know. We don't know if we'll ever know. It's weird. That's about all we have to say on the matter. Anyway, quantum gravity aside. By pulling together those various different types of fundamental particles, you can build up towards, well, non-fundamental particles. Usually the first step taken is towards subatomic particles, particularly the creation of nucleons, which is to say protons and neutrons, from those quarks. Aside from the electron, leptons don't really matter as much when it comes to physical matter. And likewise, the other combinations of quarks to create other particles don't really matter so much when it comes to, well, the building blocks of matter. After all, everything physical, or at least everything macroscopically physical, is made out of atoms. And those atoms are made out of electrons, protons, and neutrons, which is to say they're made out of electrons and quarks. So, yeah, with all that in mind, you can really sort of see how physics can very quickly branch off into chemistry. And the physics of chemistry will either be its own video or its own series / season / whatever of the Infodump. Probably what I will do is I will do a sort of shallow brush over it in this season, and then a deep dive or full-on season as either the next or a later one. Either way, the key thing to keep in mind is that for now, we can cut out all of the fundamental particles except quarks and electrons from what we need to understand as we gradually build further and further upwards towards the macroscopic scale that we all know and love. Now, when we do that, we are basically doing the same thing that a lot of mathematical equations describing physics do when they, well, switch from describing the microscopic to describing the macroscopic, or even from describing the subatomic to describing the atomic, really, which is simplify. We're taking all the variables that aren't really significant, and we're saying, okay, these are functionally zero, so we'll just ignore them. Because if we included them, this would all be far too complicated, and there's no real point because it's only a matter of, a digit changing 100 decimal places down the line, and we're not really looking that close. So, yeah. As we build upwards, we are able to understand the universe better with less rich knowledge. Which kind of makes sense, right? As these as I was talking about back at, the start of the actual mechanics of physics, so 2 episodes ago, I was talking about how as the systems become more and more complex, the different probability waves and waveforms interfere with each other to create more and more coherence and more robust coherence. Which means that as a system becomes more and more complex, as it develops more and more, the impact of anything but the cores of that coherence becomes exponentially less. So you have complex systems of very elaborate molecules made up of several different types of atoms. There's not much room for anything other than protons, neutrons, electrons, and then the force carriers for the various fundamental forces to actually have any meaning there. And the reason why I made sure to include those force carriers is because you do still get a lot of interactions there. Not so much with the weak and strong nuclear forces once you move beyond the atomic scale, although when it comes to things like, keeping your body from decaying radioactively, those are pretty important. Photons, of course, are how we gain warmth. It's also one of the ways we lose warmth. Photons are the source of all energy on a planet because, it originally is coming from the sun in the form of photons. So plants take those up, turn them into energy that they use to create more complex molecules, which they can then burn, essentially, for fuel to keep their cells alive. And then we eat the plants, or we eat the things that eat the plants, and we get all of the chemical energy that they've created from that electromagnetic energy. That is its own whole thing. Ecology will be its own series maybe at some point, or season, I guess. But regardless, when thinking about the macroscopic side of physics, we have to remember that it is a creation from the most fundamental levels of microscopic physics. These fundamental particles are all interacting and interfering with each other, and the end result is what we see around us and what we are using to see the world around us. Whenever an electrical current flows through something, we are harnessing the power of electrons. Whenever we, do any sort of experiments at advancing nuclear fusion, or whenever we power something with nuclear fission, or whatever gods may or may not exist out there help us, whenever we detonate a nuclear explosive, we are harnessing the power of, the strong nuclear force, but also of the various nucleons that it binds together. Whenever we, say, look at something, we are relying on the, electromagnetic force and its force carriers. Whenever we just exist within the gravity well of our planet, we are essentially taking for granted gravity, both for keeping our planet in orbit around the sun, which again is the source of all the energy we have on this planet ultimately, and for keeping us locked to the planet and not, inertially drifting out in space where we would instantly die. So, yeah, it all builds. And so, I just want you guys to keep that in mind for next time, that no matter how simple things might look on a macroscopic scale, it's just because we have managed to simplify them down to that point. So, next time is going to be a bit of an explanation as to how those fundamental particles and non-fundamental particles behave on a quantum level. So with that said, thank you all very much for listening and or watching, and I will see you all next time.